Hi everyone, we are Group 25 and our topic chosen is the special requirements for aerospace materials. Today, we'll be looking at aerospace vehicles, the materials used, and then zooming in onto rockets, focusing on their outer layers. So first off, what are aerospace vehicles? They are machines that travel through the atmosphere or into space, like airplanes and rockets. They play major roles in economic growth and scientific progress, but also face extreme conditions, from intense heat and high speeds to sudden pressure changes. Now, when it comes to rockets, their outer layers have to handle temperatures of up to about 3000 degrees Celsius. That's about 3 times hotter than lava. And once in space, temperatures can plunge well below zero. So, the choice of materials for aerospace vehicles are crucial, as a wrong one could result in undesired outcomes. With that, let's take a closer look at the aerospace materials and why they are so significant in structural design.
Materials used for space shuttles have to meet 4 core demands at once for peak performance. The first demand is strength. Components must withstand massive mechanical stress during launch, which is why we rely on aluminium alloys for structural integrity. The second demand is low mass. Every extra pound costs a fortune and limits our payload, hence we switch to super light but extremely strong materials like carbon fiber reinforced polymers wherever possible. The third requirement is thermal resistance. Once in orbit, materials face a brutal temperature swing, the roasting sun on one side and the bitter cold of deep space on the other. Nickel-based superalloys are essential to survive this massive thermal range. The fourth demand is that materials must withstand radiation exposure. Polyethylene can be used to protect sensitive electronics and human crews. We are truly asking these materials to be superheroes, strong, light, hot and cold-proof and bulletproof against radiation all at the same time.
So next, I'll be talking about the timeline of aerospace materials used in recent years. It is a story of continuous evolution, driven by the demands for higher performance, greater efficiency, and increased reliability. This evolution can be broken into 3 key eras. First, the metal age. We relied on aluminium and titanium, as they were strong and reliable, but heavy and limiting performance. Next, the composite revolution. Carbon fiber offered unmatched lightness and strength, leading to far more efficient aircraft. The trade-off was high cost and complex manufacturing. Today, we're in the advanced era. We use 3D printing to create complex parts and ceramic composites that withstand extreme engine heat, pushing the boundaries of what's possible. In short, our journey has been from heavy metals to lightweight composites to today's smart, high-temperature materials, each one essential for reaching new frontiers.
What exactly are the materials used on the outer layer of rockets? In rockets, specific materials form each part of the outer layer. The nozzle uses nickel-based superalloys NSAs, namely Inconel. The payload section uses carbon fiber composite CFRPs. The main body relies on aluminum alloys AAs. Stainless steel SS strengthens the propellant tanks, while silica tiles STs and ceramic composite CMCs form the thermal protection system to protect against high heat from launch and re-entry. Each material has its strengths and trade-offs. NSAs are corrosion resistant but dense and costly. CFRPs are light but brittle at low temperatures. AAs are easy to process but melt easily and prone to defects. Next, SS endures high heat but has low specific strength. ST has very low density while CMC has high temperature resistance. Both ST and CMC provide excellent insulation but are easily damaged and weigh down rockets.
Materials have completely redefined how aircraft and rockets perform. Nickel-based superalloys let engines run hotter and produce more power. That means faster speeds and better fuel efficiency. Lightweight carbon fiber and aluminium alloys reduce drag and weight, allowing aircraft to travel farther while burning less fuel. In space systems, durability is key. Stainless steel and advanced composites allow rockets to survive multiple launches, reducing cost and waste. And heat-resistant ceramics protect engines and structures during re-entry, keeping them safe and reliable over many missions. We can clearly see these improvements in today's aerospace vehicles, such as Boeing 787 and SpaceX Falcon 9, where fuel efficiency is improved by 20% and costs are cut by nearly 90%. These breakthroughs prove that advanced materials don't just build aerospace vehicles, but they drive performance and innovation forward.
Thank you.